students, welcome to Sunil's tutorial. I am Sunil Nirwani and today we will be doing this chapter called as thermodynamics. Let's see first law of thermodynamics. Let's see the first law of thermodynamics. Now the first law of thermodynamics is the same as the law of conservation of energy. That means I can say that the first law is simply nothing but the law of conservation of energy and it can be stated in different ways. First law of thermodynamics is simply the law of conservation of energy and can be stated in different ways. As follows. Now how do I state the first law of thermodynamics? There are different ways of stating the first law of thermodynamics. First method. Energy can neither be created nor destroyed. It can only be converted from one form to another. Energy can neither be created nor destroyed. Energy can neither be created nor destroyed, though it can be converted from one form to another. Though it can be converted from one form to another. Right? Whenever a certain form of energy disappears, exactly equivalent amount of energy in some other form appears. Whenever a certain form of energy disappears, certain form of energy disappears. Whenever a certain amount or certain form of energy disappears, exactly an equivalent amount of energy in some other form, equivalent amount of energy in some other form appears. Next, energy of an isolated system remains constant. Energy of an isolated system remains constant. Next, universe as a whole can be treated as an isolated system. Universe as a whole can be treated as an isolated system. Fine. That is my first law of thermodynamics. Hence, from first law, I can say that energy in the universe always remains constant. I can say hence, energy in universe always remains constant. Finally, get this in here. Now, I could also say that energy and mass are interconvertible by using Einstein's equation. Energy and mass are interconvertible into each other according to Einstein's equation. E is equal to mc square. So if I use E is equal to mc square, the equation tells me the relationship or it tells me the method for conversion of mass and energy. Finally, it is impossible to construct a perpetual type of machine. What is a perpetual type of machine? A machine which would produce work continuously without consuming energy. So it is impossible to construct a perpetual type of machine. Right? So these are the different ways in which the first law can be stated. It is the same as law of conservation of energy. Right? So that's your first law of thermodynamics. Now, let's see the mathematical equation for first law of thermodynamics. Now, heat, as we already know, is nothing but a path function. So work done by a system is also a path function. Hence, I can say that the difference between the two path function is the state function. So as I can say that, see, heat supplied to a system is a path function. I can also say that work done by a system is also a path function. Work done by a system is also a path function. Right? Once I have this, I can say therefore the difference between these two path function is the state function, which is known as internal energy. The difference between these two path functions is a state function. Is a state function known as internal energy. That means I can therefore say that internal energy is nothing but the difference between the heat supplied and the work done. Thus, I can say that the heat supplied is equal to internal energy plus the work done. That is my mathematical equation for first law of thermodynamics. Fine. Now, let's see the sign convention for this. If Q is positive, what does a positive Q mean? It means that heat is absorbed by the system. Heat is absorbed by system. That is the meaning of positive Q. Negative Q. What does negative Q mean? Heat is given out by the system. Right? Similarly, positive W is work is done by the system on the surrounding. Positive W is work done by system on surrounding. Meaning there is expansion. Right? That is positive W. Once you have this, then similarly you can have negative W. What does negative W mean? Negative W. Negative W means work is done by the surrounding of the system. Work is done by surrounding on the system. That is compression. Right? Similarly, positive delta E. positive delta E means energy is absorbed by the system. Energy is absorbed by the system. And negative delta E is energy is given out by the system. Right? Once you have this, so this is your mathematical equation for first law of thermodynamics. Next, let us see the corollary of the first law of thermodynamics.
What do you mean by corollary?
See, for example, let's assume that if A plus B gives you C, from the premises, if you get the consequent. Now from the consequent, can you get the premises? That is called as corollary. Right? So corollary is, can I get the answer from the, can I get the question from the answer? Right? Now the corollary for the first law of thermodynamics is that mechanical energy of work can be quantitatively converted into heat energy. First law of thermodynamics says that energy is converted into work. Corollary says that work can be converted into energy. Okay? So corollary of first law of thermodynamics is that mechanical energy of work can be quantitatively converted into heat energy. That is your corollary of first law of thermodynamics. Let's see numerical terms, first law of thermodynamics. Take down the sum please. Calculate Q, W and delta E. Calculate Q, W and delta E when 2 moles of an ideal gas is expanded from 15 decimeter cube to 45 decimeter cube isothermally. From 15 decimeter cube, when 2 moles of an ideal gas is expanded from 15 decimeter cube to 45 decimeter cube isothermally at a constant pressure of 2 atmosphere at 298 Kelvin. Now 15 decimeter cube can be written as 15 liters, 45 decimeter cube can be written as 45 liter. Pressures in atmosphere, so I can therefore say that work is P V2 minus V1. So work is P V2, 45 minus 15, so 2 into 30, 60 liter atmosphere. That is the amount of work done. Right? Once I know the amount of work done, then I can say we know the conversion factor that 1 liter atmosphere is equal to 24.22 calories. Hence, I can say that W is equal to 60 into 24.22. So I can say that W is equal to 14, this is calories, 1453.2 calories. That will be the work done in calories. I want the work done in joules. I can say 1 calorie is 4.184 joules. So therefore I can say that W is equal to 1453.2 into 4.184. So this will give you work done as 6080.18 joules. That will be the work done. Okay. So the first part of the question was find out the work done. I found out the work done. Since the process is done isothermally, delta T is going to be 0. For isothermal process, the change in temperature is 0. If the change in temperature is 0, that means the change in internal energy will also be 0. Therefore, I can say that delta E is 0. I know W, I know delta E. I can apply first law of thermodynamics. By first law of thermodynamics, I can say that Q is equal to delta E plus W. Delta E is 0, W you had found out is 6080.18. So Q will be 6080.18 joules. Right? Next, take our next one please. 56 grams of nitrogen. 56 grams of nitrogen is expanded isothermally. 56 grams of nitrogen is expanded isothermally at 400 Kelvin from 20 decimeter cube to 30 decimeter cube at a constant external pressure of 3 atmosphere calculate Q, W and delta E. Calculate Q, W and delta E. Right? Now, first of all, I can say that 20 decimeter cube can be written as 20 liters and 30 decimeter cube can be written as 30 liters. Once you have this, then I can say that work is P V2 minus V1. So pressure is given to you as 3 atmosphere V2 minus V1, 30 minus 20, 10, 30 liter atmosphere. Now start with your conversion. I can say but 1 liter atmosphere, 1 liter atmosphere is nothing but 24.22 calories. Therefore, I get work is 30 into 24.22 calories, which will work out to 726.6 calories. Once I have it in calories, I can convert it into joules. I can say but 1 joule, 1 calorie is 4.184 joules. Therefore, I can say work is 726.6 into 4.184 joules. Right? So when you simplify this, you will get the answer as 3040.09. Work is 3040.09 joules. So I found out work. Now I can say since the process is done isothermally, delta T is going to be equal to 0. Hence, I can say delta E will be 0. If delta T is 0, that means delta E will be equal to 0. Once you have this, then I can apply first law of thermodynamics. By first law of thermodynamics, I can say that Q is equal to delta E plus W. So Q is equal to 0 plus W, 3040.09. So Q will be 3040.09 joules. Next, take on next one please. A system absorbs 700 kilojoules of heat energy and performs some work. A system absorbs 700 kilojoules of heat energy and performs some work. If the change in internal energy is 300 kilojoules, if the change in internal energy is 300 kilojoules, calculate the work done. Calculate the work done. If the change in internal energy is 300 kilojoules, calculate the work done. Calculate the work done. Straightforward. I can say by first law of thermodynamics. First law of thermodynamics, Q is equal to delta E plus W. Substitute and you should get the answer. Very simple sum. Answer should be 400 joules. Right? W is going to be 400 joules. Next, take down next one please. By absorbing 20 joules of heat energy, by absorbing 20 joules of heat energy, the work obtained is minus 430 joules. The work obtained is minus 430 joules. Calculate the change in internal energy. Calculate the change in internal energy. Calculate the change in internal energy. Again, very simple sum. I can say by first law of thermodynamics. First law of thermodynamics says that Q is equal to delta E plus W. You have Q, you have W, you should be able to get the answer of delta E. Answer should be 450 joules. Delta E should come to 450 joules. Next, take our next one please. By supplying 600 joules, of energy, the internal energy changes by 220 joules. The internal energy changes by 220 joules. Calculate the work done in the process. Calculate the work done in the process. Calculate the work done in the process. Again, very simple sum. I can say by first law of thermodynamics. I can say Q is equal to delta E plus W. You should get the answer as W is equal to 380 joules. Right? Next. Now, let's see what we understand by enthalpy of a system. What do we understand by enthalpy of the system? Now when we talk about chemical reactions, most chemical reactions are carried out at constant atmospheric pressure. The heat evolved or absorbed at constant pressure is expressed in terms of enthalpy. So what is enthalpy? Enthalpy is the heat absorbed or heat evolved at constant pressure. The amount of heat energy that is absorbed or evolved at constant pressure will be called as enthalpy. Enthalpy is a state function. It is not a path function, but it is a state function. Fine, do we get this thing clear? State function, where its value depends only on the initial and the final values. It does not depend upon the path taken to change from initial value to final value. Right? So I can say heat absorbed or evolved, heat absorbed or evolved at constant pressure is expressed in terms of enthalpy. Right? It is a state function and it is denoted as H. It is a state function denoted as H. Right? That is what is enthalpy. Right? Now, since enthalpy is nothing but it is the heat energy absorbed, Q also stands for heat energy absorbed. So I can therefore say that enthalpy is nothing but it is the sum of the internal energy and the work done. I can say enthalpy is the sum of internal energy and the pressure volume work or pressure volume energy. Thus mathematically I can say H is equal to delta E plus PV. Enthalpy will be nothing but the internal energy plus PV. Now since E, P and V are state functions, internal energy, pressure, volume, all are state functions. Therefore, enthalpy is a state function. Fine, do you get this in here? Now, the change in enthalpy. Delta H can be calculated by the formula final enthalpy minus the initial enthalpy, where H2 and H1, or I can say where H1 and H2 are enthalpy in initial and final states. Initial and final state. Now, if I use the equation of enthalpy, I can say but enthalpy in the initial state will be internal energy in the initial state plus pressure volume P1 V1. Right? Also, I can say that enthalpy in the final state will be internal energy in the final state plus pressure volume. Right? Change in enthalpy is nothing but final enthalpy minus initial enthalpy. Right? So this can be written as E2 plus P2 V2 minus E1 minus P1 V1. So this can be written as E2 minus E1 plus P2 V2 minus P1 V1, right? Now E2 minus E1, final internal energy minus initial internal energy is the change in internal energy, right? Plus P2 V2 minus P1 V1. But since we are calculating enthalpy, what is enthalpy? Enthalpy is the heat absorbed or evolved at constant pressure. Since we are calculating enthalpy, therefore the pressure is going to be constant, but pressure is constant. Since pressure is constant, therefore I can say that P1 is equal to P2 is equal to P assumed. Therefore I can say that delta H is equal to delta E plus PV2 minus PV1. Here I could take P common, so in that case I will get change in enthalpy. Change in enthalpy is delta E plus P V2 minus V1. So change in enthalpy is delta E plus P delta V. V2 minus V1 is nothing but the change in volume, right? So that's my equation for enthalpy, change in enthalpy. Delta H is equal to delta E plus P delta V, right? Now, let us see what is the enthalpy in different types of processes. In different processes. Now, first let's consider isobaric process. Now, for an isobaric process, we already know that enthalpy we've just derived. Enthalpy delta H is equal to delta E plus P delta V. We just derived, right? By first law of thermodynamics, if I apply first law of thermodynamics, I can say that Q is equal to delta E plus W. But we know that W is equal to P delta V if P is constant. So if I apply this, I will get heat at constant pressure is delta E plus P delta V, right? Delta H is also delta E plus P delta V. QP is also equal to delta E plus P delta V. Therefore, comparing the two equations, that is comparing equation 1 and 2, I can say comparing equation 1 and 2, I can say that QP, heat at constant pressure, is equal to the enthalpy. Right? Next, let us consider an isochoric process. Right? What is an isochoric process? In an isochoric process, I can say that delta V is 0. Since it is an isochoric process, therefore volume is going to will be constant. Now, if delta V is 0, therefore I can say that P delta V will also be 0. If the change in volume is 0, that means P delta V will be 0. Hence, enthalpy delta H, which is equal to delta E plus P delta V, will be delta H will be equal to delta E. For an isochoric process, enthalpy will be equal to the internal energy because no external work is being done. Now, by first law of thermodynamics, If I apply first law of thermodynamics, first law of thermodynamics says that Q is E plus W, right? And but W is equal to P delta V. So for an isochoric process, QV, heat at constant volume, will be nothing but delta E plus P delta V, but delta V already we know is 0, so QV will be equal to delta E, right? So for an isochoric process, enthalpy is equal to internal energy, and heat at constant volume is also equal to the internal energy, right?
Q is equal to delta E plus W.
Which one? Q is equal to
Delta E plus
delta E plus W. Fine. Next, let's consider an abiotic process. Let's consider an abiotic process. Now, what is an abiotic process? An abiotic process is the one in which heat at constant pressure, which is equal to enthalpy, is equal to 0. Right? In which case, for an abiotic process, but we know that enthalpy is change in internal energy plus P delta V. So in that case, I can say 0 is change in internal energy plus P delta V. Right? Therefore, I can say that change in internal energy is negative P delta V. Fine, do we get this? So these are the different form. This is enthalpy for different processes. Fine, do we get this in here? Next, let us understand what is thermochemistry. Now, what do we understand by thermochemistry? Thermochemistry is that branch of chemistry which deals with the study of enthalpy. Right? A branch of chemistry that deals with enthalpy changes in a chemical reaction is called as thermochemistry. Right? So it is a branch of chemistry. It is a branch of chemistry that deals with the study of enthalpy changes in accompanying a chemical reaction. So what will be the enthalpy changes in the chemical reaction? You study all that in thermochemistry. So the main aim of thermochemistry is to determine the quantity of heat evolved or absorbed in various processes. Main aim of thermochemistry is to find the quantity of heat evolved or absorbed in various processes. That is what is thermochemistry. Next, let's see the different types of reactions that you have. What do we understand by exothermic reaction? Now, in any chemical reaction, the initial state and the product state. Change in enthalpy is nothing but the difference between the initial and final energy and the initial energy, right? So therefore I can say that change in enthalpy is also written as the enthalpy of the product minus the enthalpy of the reactant change in enthalpy can also be written as the difference between the enthalpy of the product and the enthalpy of the reactant. Right? I can say that in a chemical reaction, change in enthalpy is nothing but the enthalpy of the product minus the enthalpy of the reactants. Right? Now, delta H, that is your change in enthalpy, can be positive or negative. Delta H can be positive or negative. Now, depending whether it is positive or negative, it will tell you whether heat has been absorbed or it has been evolved. Right? Now, if delta H is positive, then the reactants have absorbed heat and got converted into product. Right? If delta H is positive, that means the reactants must have absorbed heat and got converted into product. Moreover, if delta H is negative, instead of positive, if delta H is negative, that means the reactants have lost heat and got converted into product. Such a chemical reaction in which the enthalpy decreases, that means the enthalpy of the reactant is more than the enthalpy of the product, is called as an exothermic reaction. Right? What is an exothermic reaction? If delta H is negative, then enthalpy of products is less than enthalpy of reactants. Right? That means the reactants have lost heat and got converted into product. Therefore, reactants have lost heat and got converted into products. Such a reaction is called as an exothermic reaction. So I can say that a chemical reaction in which the enthalpy decreases is known as an exothermic reaction. Right, that is what is an exothermic reaction. Next, what do we understand by an endothermic reaction? An endothermic reaction, a reaction in which the enthalpy of the reactants is, you have a change in enthalpy is enthalpy of the product minus enthalpy of the reactant. Now, if the enthalpy is positive, that means the reactants have absorbed energy and got converted into product. Such a reaction is called as an endothermic reaction. Right? I can say when change in enthalpy is positive, that means reactants have absorbed heat energy and got converted into products. Right? Reactants have absorbed heat energy and got converted into product. Therefore, I can say that Here the enthalpy of products is greater than enthalpy of reactants, right? So a chemical reaction in which the enthalpy increases is called as an endothermic reaction. A chemical reaction in which enthalpy increases is called endothermic reaction. Right? Now, once I know what is endothermic reaction and exothermic reaction, let us find out what do you understand by a thermochemical equation. What do we understand by thermochemical equation? Thermochemical equation, the equation representing the conversion of 1 mole of reactant into product, indicating the amount of heat energy absorbed or evolved under standard condition is called as a thermochemical equation. A chemical equation which shows the conversion of 1 mole of reactant into product, indicating how much heat energy is absorbed or evolved under standard condition is called as a thermochemical equation. I can say that the equation representing the conversion of 1 mole of reactant representing the conversion of 1 mole of reactant into the products and indicating the evolution or absorption of heat under standard condition, indicating the evolution or absorption of heat at standard under standard conditions is called thermochemical equation. Let's try to explain this to you with the help of an example, right? For example, if I give you a equation like this, say methane in gaseous form reacts with 2 molecules of oxygen in gaseous form to give you carbon dioxide and water. In liquid form. Delta H at 298 degrees is minus 890.3 joules. This equation would be a thermochemical equation. In this equation, you have taken 1 mole of reactant and converted it into product. It is also telling you how much amount of heat energy has been absorbed or evolved. And this is the amount of heat energy that has been absorbed or evolved under standard condition. Standard condition means at NTP, normal temperature and pressure. Normal temperature normal pressure is 1 atmosphere and normal temperature is 298 Kelvin, right? So do we understand this? Now let us see what do you understand by heat of reaction. Now, heat of reaction is the difference between the enthalpy of the product and the reactant at constant pressure at any given temperature when every substance is in standard state. So, heat of reaction is nothing but it is the difference in the enthalpy of products and reactants products and reactants. It is the difference between the enthalpy of the products and reactants in a reaction at constant temperature. In a reaction at constant pressure. And at a given temperature, at constant pressure and at a given temperature when every substance is in standard state. When every substance is in standard state. That is what is called as heat of reaction. So heat of reaction is the same as the change in enthalpy, right? Now let us try to get an equation, or let's try to get a relationship between heat of reaction at constant pressure and constant volume. Relation between heat of reaction at constant pressure and constant volume. Now we know from enthalpy for different processes, from enthalpy for different processes, we know that change in enthalpy is nothing but heat absorbed at constant pressure, and change in internal energy is heat absorbed at constant volume, right? But change in enthalpy is nothing but change in internal energy plus P delta V, right? Now P delta V can be written as V2 minus V1. Delta H is delta E plus P delta V. Delta V can be written as V2 minus V1, right? So therefore I can say that delta H is equal to delta E plus PV2 minus PV1. But by Gass's law says that PV is equal to nRT. Gass's law says that PV is equal to nRT. Therefore, I can say that PV1 will be nRT1 or N1RT, because you are saying at constant temperature, and PV2 will be N2RT. Therefore, I could say that the change in enthalpy, which is also called as heat of reaction, is delta E plus PV2 is N2RT minus N1RT. Therefore, the change in enthalpy is delta E plus N2 minus N1RT. Thus, I could say that the change in enthalpy is delta E plus delta nRT. N2 minus N1 is nRT, but delta H, change in enthalpy, is nothing but the heat absorbed at constant pressure, and change in internal energy is the heat absorbed at constant volume. Therefore, I can say that the heat absorbed at constant pressure is equal to the heat absorbed at constant volume plus delta nRT. That's my relationship between heat absorbed at constant pressure and heat absorbed at constant volume, right? We'll stop this here for the day. Thank you very much.